We're going to get right into 2.1, which is instantaneous and average rate of change. So average rate of change, if you look at rate of change, it's really about the slope. And as I've covered with you, it's a slope of a line. Okay. I have an excellent tool that explains various things. There's one that has just shows maybe I should turn off the red. Turn off the red graph, or the blue graph. It shows a cubic curve, and it's showing the rate of change at any one moment. That's instantaneous rate of change, but that's actually pretty complicated. And let's see if there's a different one here. Oh, there we go. So this one shows a sine curve, or parabola rather. So just ignore the red and the green lines. Red and the purple lines. There we go. So here we have a parabola, and what I've done is, I think that's my instant rate of change. And what I've said before in the last video is you can measure average rate of changes between two dots. And once you figure out which two dots you want to measure, you can then join a connection, straight line between them. And the reason you do this is because you can figure out the slope of a straight line very easily, but you can't figure out the slope of any other line. So anytime you can use a straight line, you can figure out the average rate of change, which would be essentially the average slope between this dot, this red dot, and this green dot. So what's the average slope along the parabola for that? As you can see, this average rate of change can be very accurate on the steeper parts, but a little less accurate when here you see the big gap between the red line and the black line. So that's not quite average, and it really goes non-useful when it jumps to the other side of the curve. And that's because the other side of the curve has a totally different slope going downwards. But one thing you can notice, so then the other thing that you want to learn how to measure is not the average rate of change, but something called the instant rate of change. And that's when you put a tangent line straight through the specific dot you're looking at. So if I want to see the instant rate of change right here at this dot, I draw a tangent line, which is essentially a line as best fits that's 90 degrees from that dot. And it gives me an instantaneous rate of change. In other words, the slope exactly of that dot. Now I want you to look at something. Notice the slope here is positive. The slope, sorry, it'll be negative here, and I actually put the slope somewhere. Yeah, right there. No, that's for these two dots over here. There it is here. So that's the slope of this line. Notice it'll change as I go down, and it gets quite steep. The numbers get quite big as I go way down this slope. And they ease off as I approach the top, and that's because the top is a horizontal line. See this here? Watch how it changes. That's because the top is a horizontal line, and at the horizontal line, the slope's going to be 0. There, almost there. If I zoom in, I can probably get the top almost perfectly. There we go. The peak, that's 0. And then when I go down the other side, you'll notice the slope is positive, and that's because this line is going up from left to right, and it gets bigger and bigger slope. And it's very hard to draw this line perfectly. But what you're going to discover, and I'm going to go back to the red line, is if you pick two dots. Oh yeah, so first I want you to notice the slope at a specific spot here. I want you to notice the slope. Let's pick at 1. So that's an x value of 1 and 1 comma 6. And the slope is beautiful 2. So I want you to remember that. At 1 comma 6, the instantaneous rate of change is 2. And you might say, what? Huh? What? How do I calculate? Never mind that. That's essentially the exact slope at that point. Now I'm going to go back to the two dots. Okay, I'm going to get rid of this dot for a second. And I'm going to draw this line, which is essentially, there we go, these two dots way up here. And now I'm going to put these two dots on either side of 1.6. I'm going to put one way up here at the peak and one way down here at the bottom. And it would help if I put them equidistant on the left and right, but it doesn't really matter. Notice the slope of the red line. That's indicated right up here. It's 1.86. It's pretty close to 2. It's not too bad, but it's hardly accurate. Now watch what happens when I make these lines further apart. That slope gets way off from 2. At one point it matches it, but overall it's not too accurate. It's not hitting it. But as the dots get closer and closer to each other, I want you to notice the M here compared to the M here. So if I bring that down, I'm going to just zoom in now. And that's the dot we're trying to approach. That's 1.8. And bring the 2 dots closer. It's 1.9. It's almost 2. I'm going to bring it closer. The 2 dots closer. And I'm bringing them closer on either side of 1.6. Oh, it's 2.015. That's very accurate. Now I'm going to bring them even closer. Notice, though, when I zoom in, the red line's not quite on the graph, so it's still not totally accurate. But as I get those 2 dots closer and closer, they start getting really, look at that, 1.999. They start getting really close to the actual slope at 1.6, which I cheated and told you was 2. And the closer you can get those dots to the actual point, the more accurate your slope is. So the reason we're learning average rate of change, which is just a secant line is a straight line drawn between 2 points on a graph, is so to learn that as you get closer to the coordinate you're interested in, which is 1, 6, you can learn how to get an accurate idea of the rate of change. Why are we doing this? To show how other formulas are derived, how we come up with instant rate of change as we get closer to that, how we come up with a tangent line, and then that leads into calculus. So just ride along for now and just try to realize we're trying to come up with the accurate slope of a line that would represent the slope on this black graph at 1.6. And by doing that, we often start with the average rate of change, which is the slope between 2 points on this graph. Okay, and as we get closer and closer to our point of interest, the slope of our secant line, which is the line between 2 points, will approach the actual slope of the tangent line. Right there. So it'll get closer and closer to the actual purple line as I bring the values, the 2 dots closer. I'm going to zoom in. Notice how close the red line is to the purple line. I'm going to zoom in. Bring it right close. My purple line and red line are almost right on top of each other. Really close. So much so that I'd have to zoom in really tight, and they're still almost, red and purple are almost overlapping. And as I get very close, you will see that my secant line and my tangent line are pretty much on top of one another. There it is. I have to zoom in a lot to see a difference. And that is the point we're trying to learn. We're trying to learn how to do average rate of change, which is quite easy, to come up with estimates of instant rate of change, which is an exact slope at a specific spot. Hope that helped. I'll provide a link to that tool later. So it walks you through how to do an average rate of change. Well, the idea is you take 2 points, so there's an x and a y there, and there's an x and a y here. And you take the delta y between these 2 points, 6/1954 and 0/8/15, and the delta x, and you come up with a slope between those 2 points. And let's say you're trying to come up with an exact slope at this point here. Well, if you take the slope of 2 points on either side of it, you will get a fairly good approximation of what's going on. So to show you that in drawing, if I have a ski hill, or I'm climbing a hill, or this graph, doesn't really matter how I want this to draw this graph, and I'm trying to get an idea of what the slope is right there on this hill, like how steep is that, I'm going to take points around it, here and here. I'm going to draw a straight line between those points. And And then I'm going to figure out the slope of that line. Didn't quite get it, by the way. I'm going to take the slope of that line to figure it out. Then I'm going to take 2 points even closer. I'm going to draw a straight line right through those again. And that's called a secant. And I'm going to take the slope of that new line. You can see I'm getting very close to the actual tangent. And I'm going to keep doing that until I get a line that pretty much looks like the tangent line. And that's what they're trying to get you to do. So you got to start with points that are far away, and they might even ask you, what's the overall rate of change between this whole graph? And that's when you take the last point and you delta y, delta x it with the first point to give a total average rate of change. Then they explain average rate of change over here. And then they give you an example of how to take, so they give it right here between 0 and 2 on the x, which is 0 and 2, and you're taking a delta y, delta x between those 2 points. Then they're doing it again between 2 and 4, between 4 and 6, between 6 and 8, and 8 and 10. And you can see that your slope of the line between those 2 points is getting steeper and steeper. And that ends up being the rate of change of how many bacteria grow per hour at that between those specific time periods. It'll become more clear with practice. So here's a slope, right? They ask you to draw a secant line between those 2 points. And then you're trying to estimate 2 points on that red line and taking the slope of it. They give you a few examples and they explain it. They ask questions like, why is the average rate of change of bacteria population positive on one interval? And how is it recanted on the secant line? So positive would mean that the bacteria are growing with time. Negative would mean the bacteria are decreasing with time. How is calculating an average rate of change like calculating the slope of the secant line? It's almost exactly what you're doing. Why does rate of change have units even though slope does not? Well, I guess slope can be looked at as just the number, as how steep it is, whereas rate of change is how quickly things change. Like how fast does your car move? It changes in kilometers per hour. You'd never say, if I said, how fast are you driving? You'd never say, well, you would say 100, and I would know what you mean. But it helps if you tell me 100 kilometers per hour. Why is the rate of change in the bacteria population not a constant? Well, that comes up with your knowledge of growth. So bacteria, when they double, they've got 2. But when I double again, I've got 4. When I double again, I've got 8. When I double again, I've got 16. When I double again, I got 32. And on a graph, that's like that. And that's because every time you create a living creature, it can, for bacteria anyway, it can split into 2. And bacteria is one of the fastest growing living creatures around. It's why when you get sick, it's very important to see a doctor right away, because it can grow fast enough to kill you, especially if you're older, before a doctor can stop it. We treat bacteria with antibiotics, and which is good. However, if you have a thing like a virus, the only thing we know how to treat a virus is with a vaccine. So vaccines take longer to develop, and antibiotics can be used for we have antibiotics for almost every bacteria we know of. And bacteria is always in a growth curve. So are things like deer population, any animal population, human population. That's because your parents have kids, and those kids have kids, and those kids have kids. And it's very rarely one kid has one child. If you have a couple, you usually have 3 or more kids, which means that 2 people became 4 people. Things like that are just common sense, and they tie in with your biology. So here we see she rents a car. She's charged $35 a day, plus this much for each kilometer, which means you can see right away she's going to start at 35. And the longer she drives, which is on the x-axis, the more she gets charged, which is on the y-axis, which makes sense. So she gets charged an extra 15 cents per kilometer. per distance, 15 cents a kilometer. So if she drives 10 kilometers, she gets charged $1.50 more. If she drives 100 kilometers, she gets charged $150 more. So let's see if we can find that in a graph. So if she drives 10 kilometers, it's going to be $36.50. We can't quite see it because it's right there. But there, let's do the 100 kilometers. If she drives 100 kilometers, it is going to be $15, which should be 50. So on this 100, there it is, $50. So her rate of change is consistent, which is going to be the slope, 0.15. So no matter where I take the slope on this line, that will be both her average and her instantaneous rate of change, because it's consistent no matter where I am on the line. But here they're getting you to do a delta from the very end, from the very beginning, delta y and delta x, but they call it delta cost over delta distance. And they just show you that the slope is the same no matter where you take it. Then they do another example of a draining tub. You can see that this draining tub drains slower and slower as the volume, probably because the volume causes it to drain quickly and then it drains slower. This is called a decay curve, in that each volume halves from the last one. Calculate the average rate of change. So instead of doing this, those are good examples to review. We're going to go straight to the question. And then using the equation to determine the average rate of change. So the equation is definitely, now you might say, hey, that's not delta y and delta x. You're right. They're taking the x values or time values from 0 to 1, and then they're taking the y values in function form. That's essentially y when x is 1. And then that's y when x is 0. So they're just revising the delta y, delta x formula. And let's see where they came. Let's see if we can come up with a good explanation. Let's use Desmos. So if I have a normal parabola, y is equal to x squared, and I take a table formula, and let's just work with the positive values. And there we go, over here. And I'm going to label these 4 dots. And they all make sense if you know your parabola. Oops. So if I take, let's focus on 3, 9 and origin, 0, 0. 3, 9 and 0, 0. If I take my delta y, delta x, I'm taking 9 minus 0 over 3 minus 0. And that's pretty clear. It's 9 over 3. It's 3. Which means the secant line, or the slope, if I draw a straight line between those 2 points, between there and there, that slope of the green line is 3. Now, let's put it in the new version. What if I said, well, I'm taking it between x3 and x0, so the bottom is still 3 minus 0. But instead of writing 9 and 0, I'm doing f of 3, which means the y value when x is 3, minus f of 0, which means the y value when x is 0. You'll discover that's the same thing, because f3 is 9 and f0 is 0. So it's still 9 minus 0, but now I've written in terms of a function instead of the y values. Instead of delta y, it's now written as f of x2 minus f of x1, all of it divided by the actual x2 minus x1. So the delta x hasn't changed, just the delta y has been revised, and it's just revised in function form. Okay, now that doesn't matter what dot I take it in. Suppose I take it between these dots, 2, 4, and 0, 0, and I draw a straight line between those. And the delta, actually let's take it between this line and this line. And we're going to do it in function format. So I'm going to, the x value of this is x2 is 2. So it's x2 minus x1. Between those 2 dots, that is the same as 2 minus 1. Up top, I'm taking the f of x2, minus the f of x1. Now you can either plug that into the formula over here and figure that out, or, so that's essentially going to be f of, what's the y when x is 2, and what's the y when x is 1, and just remember that they're both being divided by these things, like that. And that means you've got to figure out what f of 2 is. Well, f of 2 is 4, so you get 4. And f of 1 is 1, so 4 minus 1 over 2 minus 1, which is 1, 3. So you can see the slope here is also 3, which I believe was the same as that slope, interesting enough. So it's safe to say that the halfway point between those will also be 3. But you can see that it's just a different notation for taking delta x and delta y. Delta x has stayed the same. Believe it or not, delta x is going to eventually change into something called h, which just means a difference between these two x's. We'll get into that soon, but they're all the same thing. This version of slope is the same as this version of slope, which is called rate of change, and it's still slope. Okay? Don't get intimidated by it. Let's just jump. So they give a nice summary here, and they show you what the old slope was, and they tell you what you need to know. So calculate the average rate of change for the function. So what are we dealing with? We're dealing with an upward facing parabola. 4x squared minus 5x plus 1. So I'm going to just use 4x squared minus 5x minus 1, which I believe was what was used. And I'm going to just take a nice carbon copy of that. I'm going to go to here and just paste it. Like, let's just do the first two. We'll leave space. And fortunately, they've used the same graph for each of the questions. Now I'm going to also add the whole thing on the next, and I'm also going to put it in that format. And I'm just going to give a slightly different one here, because I'm going to make the second one into a table. And we're going to deal with, are they dealing with 2 to 4, 2 to 3, and 2 to 2.5? 2 to 2. So they're getting closer and closer to 2. See that? They're getting closer and closer to 2. See how close the 2 is? So in this case, it's not a bad idea to, let's put f of x instead there. It's not a bad idea, and we'll just put 2. And we're working with 4, 3, I think we're working with 2.25 and 2.1. It's also not a bad idea to have down here, you can always just punch in what is f of 2, and it's going to give you the y value when x is 2. So this is a very useful thing to save yourself some calculations, okay? But you can always make a table of the values they're looking for. We're looking for 2.01, they're also 2.1, and they're also looking for 2, 4, 3, 2.5, 2.25, 2.1, 2.01. Okay. So if I'm going to do them all, I can do 2, 4, 3, 2.5, 2.25, 2.1, and 2.01. All right. So we're just going to print that. And we're just going to work with things one at a time, okay? Take this. And you know what? All I need is really the formula for now. Just be aware of what we're looking at. We're looking at the slope in this rough area, and we're trying to get close to where x is 2. Okay. Okay. So the first thing they ask you is find the average rate of change, or slope, essentially between when x is 4 and 2. So here's 2 and here's 4. So how we write that is the rate of change, average rate of change, ROC, and you're going to get used to that, bring AROC, is going to be f of 4 minus f of 2 f of x2, there we go, minus f of x1 divided by x2 minus x1. Okay? All like that. So ask yourself, what's my x1 and my x2? Well, in this case, they're looking for the difference between 4 and 2. So my second value, which is usually the bigger one, is 4. So that means I'm going to rewrite this as what is my f of 4 minus my f of 2 divided by 4 minus 2. You can see one of the good reasons to write it this way is you don't mix up your x and your y values. And now all I need is to know what is f of 4 and what is f of 2, because clearly 4 minus 2 down here is going to be 2. So I just need to know my top part. Well, f of 4 is 43, f of 2 is 5, so you get 43 minus 5 divided by 2. 43 minus 5 is 38 divided by 2, which is 19, which means between these two values, the slope is 19, positive 19, which means it's sharp like that. Okay? So we have an average rate of change between 2 and 4. So somewhere we would write down A, and we would show our work too. A, average rate of change between x, and we just 2 is equal to x smaller or equal to 4, is 19. Okay, now we go down to the next one, B. Next, they want to see what's the rate of change between 3 and 4. Well, okay, the only thing that's changed here is your x and y values are not 4 and 2. They're now 3 and 2, not 3 and 4, 3 and 2, which means I'm not looking for f4 here, f of 4, I'm looking for f of 3. So we know that 3 minus 2 is 1, so the bottom's going to be 1. The question is, what is f of 3 minus f of 2? Well, f of 2 is always going to be 5. F of 3 is 20. So we get 20 minus 5, which is 15, divided by 1. So the rate of change is 15. So we will mark that down. My average rate of change between those 2 points, between 2 smaller or equal to x and smaller or equal to 3, is 15. So it's getting a little less steep. Next, we're going to go to C, my average rate of change between 2 and 2.5, essentially. Well, we know that the bottom x1 hasn't changed. It's still 2. It's always 2 in all these examples. But now my new x2 is 2.5. So now the bottom is 2.5 minus 2, which is equal to 0.5. Now all I have to do is figure out what is f of 2.5 minus f of 2. And again, I have to look over here. Well, f of 2 is always going to be 5. And what's f of 2.5? Fortunately, I wrote it down, 11.5. 11.5 minus 5 is 6.5. So you get 6.5 divided by 0.5, and you're going to discover, if you use your calculator, that's 13. Which means my average rate of change between 2 and 2.5 is 13. Next, we're going to find the average rate of change, D, average rate of change between 2 and 2.25. And we're going to do these calculations over and over again. Some things are going to remain consistent. So the delta, the x1 and the fx1 are always going to be 5 and 2. Now, what is f of 2.5? So it's going to be 2.25 for x minus 2. And what's the f of 2.25? Well, it is right there, 8. 8 minus 5 is 3. 2.25 minus 2 is 0.25. Now I want you to notice that the thing we're dividing down by here is getting smaller and smaller as we get closer and closer to the actual 2 value, which is what we're seeking, the actual 2 value rate of change. So we get 3 divided by 2.5, and you're going to discover that's the same as 12, which means the average rate of change between 2 and 2.5 is 12. Looks like we're approaching some number because it went from 19, 15, 13, 12. The differences are getting smaller. Then we're going to go on to the next part. And the next part says, what's the average rate of change between between 2 and 2.1. So again, some things don't change. My x1 is always going to be 2, and my f of x1 is always going to be 5. And the question is, my x2 now here, sorry, my x1 is always going to be 2, and my f of x1 is always going to be 5. The question now here is, what's down below is 2.1, and what's my f of 2.1? Well, fortunately, I wrote it down here, 6.14. So now I have to subtract 6.14 minus 5 up here, and I get 1.14, and I have to divide it by, what's 2.1 minus 2? 0.1. And you're going to discover that this is 11.4. So that means my average rate of change between x values 2 and 2.1, 2.1, yeah, is 11.4. All right, geez, we're kind of approaching 11. So now we're going to this last one to do, which is very small distance between 2 and 2.1. So we're going to do, again, x1 is always going to be 2, and f of x1 is always going to be 5. And here we're subtracting 2.01, and all we need to do is find the f at 2.01, which fortunately I've taken right there, is 5.1104. Okay, so when I subtract the top, I'm left with 0.1104, and when I subtract the bottom, I'm dividing it by 0.01. And you're going to discover this is the same as 11.04. Which means finally, as I got really small here, the rate of change between x of 2 and x of 2.01 was 11.04. Which number am I approaching? As I get closer and closer, I went 19, 15, 13, 12, 11.4, 11.04. What number do you think I'm approaching? It looks to me that I'm approaching 11. So I can make an educated guess and say, I bet you the instantaneous rate of change right at 2 is 11. Now, if I were to cheat and go back to that little tip I gave you the last one, and I was to take the derivative of this, so the 2 comes down, it's going to multiply the 4, and I get 8x. And the 1 comes down and multiplies the minus 5. It becomes minus 5 times x to the 0, which is just 1. So I get 8x minus 5. If I put a 2 in there, what's 2? Because I'm trying to find instantaneous rate of change at 2. What's 8 times 2? 16. Minus 5. Oh, I might have made a mistake somewhere. 18. 8x minus 5. 16 minus... Oh, yeah, sorry. No, 8. 16 minus 5. It is 11. There we go. So I can see that 16 minus 5 is 11. Indeed, probably I can see from cheating using calculus that indeed the instant rate of change at 2 is indeed 11. But this part just skip for now, but I'm just trying to help you show how it's leading into calculus. This is called a derivative. Okay, so all we're learning is if we take dots that are close and closer to each other, we're approaching the average rate of change approaches what's called the instantaneous rate of change. The average rate of change gets closer and closer to instant rate of change. Essentially, you're getting closer and closer to that tangent line that we're eventually going to be seeking. All right. Let's go on to the next question. And always use your Desmos to speed up your work if you understand what's going on. Okay, let's look at this. And let's try to figure out what's going on in it too. I'm just going to take number 2 and number 3. So an emergency flare shot into the air. And you can pretty much be sure that most things shot into the air go up, hover, and then come down. But let's just try to figure out the graph on this. What's happening at 0 seconds? It's 2 meters off the ground. So it's some guy who's standing 2 meters off the ground. So right there at 2 is our start, 0, 2. At half a second, wow, it's way up here at 15. What's the max height, by the way? Looks like 47. And there's some matching heights, and there's some matching heights. And you can probably get more matching heights. And you can pretty much figure out when it would hit the ground. If this is the max height at 3, if the max height happens at 3, what do you think happens at 6? It probably hits the ground at 6. So you can take an educated guess that halfway up is 3 seconds, so all the way down will be 6 seconds. However, that's not exactly true. That would be true if we started at 0, 0. Because we started an extra height, it might go a little bit longer. However, it is safe to say that from 2 meters height, 3 seconds later it hit its max height of 47. It is safe to say at 6 seconds it's going to reach the height it started at. So at 6 seconds it's going to hit 2, which means a few seconds later it's going to hit the ground, or 0.0 seconds. But anyway, they're showing us in intervals of half a second the height. So it's definitely a downward facing parabola, and we could actually even figure out the formula. Determine the average rate of change between this interval, 1 second and 2 seconds, 3 seconds and 4. So I already told you that the 3 is the peak, because you can even see it from the numbers here. It's going up and up and up until it hits 3, and then it's going down and down. Which means that between 1 and 2, which is here, the slope is going to be positive, and between 3 and 4, it's going to be coming down, the slope's going to be negative. And that's what we're going to find out. But we need to take average rate of change between those points. Okay, so let's start with the information we're given here, and they want us to figure out the average rate. Oh. So we want to see average rate of change between 1 and 2 seconds, which is here and here. And you can even see the y values. They pretty much give you the y values. So if we were to write it in delta y delta x, 2 minus y1 over x2 minus x1, we can see that that becomes 42 minus 27 divided by 2 minus 1. What's 42 minus 27? It is 15. And what's the bottom? 1. So 15 divided by 1, 15. Positive 15. So we can see on its way up, we get a rate of change of 15. So it's definitely a fairly steep slope here. Let's look at our rate of change at our next times. Our next times, they're looking between 3 and 4, which means our delta y is going to be 42 minus 47. So it's clear already that's going down. 42 minus 47 is going to be creating a negative. And 4 minus 3, which is x2 minus x1, is 1. So what's 42 minus 47? It's negative 5 divided by 1 is negative 5. So we can see from 3 to 4 it's starting to fall. We can also see from the number 5 is much smaller than 15, which is what we got here. So therefore it's starting to come down, and we can tell it's coming down from the negative. So with plus 15 we could tell it's rising sharply, and with negative 5 we can see it's starting to fall down. Use your results from part A to explain what is happening, and we just did that. Given the function f of x and g of x shown on the graph, discuss how the average rate of change differ in each relationship. Okay, for that we need the graph. Here we go, there's the graph on the left. And we'll go back. So I hope that last one, the flares, understood. Okay. Okay, this is a straight line. f of x, x plus 3. So it's easy to see the slope of this line. There's a 1 in front of that x, which means the red slope m of red line equals 1. Discuss how the average rate of change differ in each relationship. Well, the average rate of change for the line will always be, the AVOC will always be 1. But the rate of change for the blue line, if I look at drawing the lines between this part and this part, this part and this part, and this part and this part and this part and this part, is that the rate of change on this left side of the parabola will be negative, and it'll start as big numbers like negative 15 and then negative 5, and then as it reaches the bottom it'll be 0. And then on the right side of this graph, we're going to have positive slopes as the parabola starts going back up. So positive. So this is called intervals of change, actually. And that means on the left side of the vertex, I have decreasing intervals of change. And on the right side, I have increasing rate of change. Positive, increasing. Negative, decreasing. And that's how they differ. So which means that this is point 0. When x is 0, this is how you would write it for the blue line. When x is smaller than 0, rate of change for blue line is negative, decreasing. That would be called an interval of decrease. When x is exactly 0, there is no rate of change. It's flat line, it's a tangent, so no rate of change. And when x is bigger than 0, the rate of change is positive, or an interval of increase from 0 to infinity. That first one would be from negative infinity all the way to 0, but not including 0. When it's smaller than x or smaller than 0. So that's an interesting thing to distinguish, that at the vertex suddenly the rate of change changes. There we go. Let's see if I have, so they're getting you to practice the average rate of change again for each half hour of the rally. So let's look at what's going on. After the first half an hour, there's 176 people. Then after another half an hour, it looks like they added about 70 people. Then after another half an hour, it looks like they added 130 people. Then after another half an hour, they only added 12 people. And after another half an hour, they only added 30 people. And after another half an hour, the crowd started getting smaller. So it looks like there was a very quick arrival. Then it starts tapering off to 432, which was the peak, and then it starts going down. Which, if you're going to draw that graphically, all that means is, as time increases, the crowd goes up to a peak, and then they start leaving again. And you notice right here the crowd increases a lot quickly, then slowly, and then they start to leave, which is normal for any event. Tons of people show up at a certain time. All right. Now, to do the average rate of change, you would do delta y over delta x, and we can sort of do a few of them. And we'll just do number 4. I'll just do one question at a time. Okay. And I'm going to try to stick to doing all of them, even though it takes a long time. But once I do it once, it'll be documented. So let's take it between these two. So what's the delta x between those two? Half an hour, or 0.5 hours. What's the delta y? 176 minus 0. Okay, so let's do that formally. From 0x to 0.5x, or in this case it's called time in hours. The delta t, because it's time, is 0.5. During that time, for those values, y1 is equal to 0, and y2 is equal to 176, which means we're looking at 176 minus 0 on the top, which is the delta y, and 0.5 minus 0, which is that, which is going to equal 352, which means the rate of change between those values, the rate of change here, average rate of change, the AVOC between those is 352. So it's quite a steep slope, and it's positive. Positive. Then they want you to do it for the next group. Notice that the average, the delta x for all of this is going to be 0.5 every time, or delta t 0.5, which is the same as delta x. And what's the delta y? Well, the delta y is 245 minus 176, which is 69. 69. So then the slope, or the AVOC, is going to be equal to 69 divided by 0.5, which is equal to 138. So there, I can just get rid of all that and just say the AVOC between that is 138. Okay. Then they want you to do for the next group. Now you can see how this is tedious and all that, but it's still good practice, because that's when you practice these things, that's how you will never make mistakes on tests when you do these over and over again. Which means the delta t is still always 0.5, and the delta y here is going to be 388 minus 245, which is going to be equal to 143, and which means the average rate of change is going to be 143 divided by 0.5, which is the delta y divided by delta x, which is 286. So there, the average rate of change is 246 for that interval. And you notice over and over again the delta t is the same. And then they ask you to do it again. Really, the big change comes when the peak of the crowd stops. So I'm going to just get rid of this, because I think you're following along so far. I'm just going to move it up. And that's a 1 that's supposed to go up here. Okay, and this next one, we'll just put it there. And we'll keep in mind that the delta t time difference is always 0.5 in these examples. And the next one and the next one. And that the average rate of change is going to be the delta y, which is 402 minus 388. You can see the number's going to get smaller right here, which is 1214 divided by the delta x, 0.5, which is 28. So suddenly the average rate of change went from huge numbers to small number. So it was 352, 136, and then it jumped up again, so a big crowd came between this time. So what you're going to see is a thing that kind of goes off and then steeps and then tapers off, peaks, and starts to fall. So you're going to have this weird graph, which is more true to real situations. But so it was big, got a bit smaller, got huge again. This slope is not as big as that slope, so this part here is much steeper. And then it starts to taper off. And then the next delta change will be from 2 to 2.5, which is right here. And you can see the crowd only grows a tiny bit. And so the average rate of change, AVOC, is going to be delta y, which is 432 minus 402, which is 30, divided by the consistent delta x, which is 0.5, so 60, which means the rate of change in that time interval will be 60 people per hour. And then finally, the last one is where we see people start to leave. And they include this to show you what happens to the slope. So pay attention to the slope on this one. The average rate of change is going to be delta y minus 432. Now notice you can't use the biggest number minus a small number. You always have to use the next value of y on the chart. So, and that relates to 3. The 415 relates to 3 minus 2.5, which relates to the 432. You can't mix that up because you're going to get a wrong result. Down below it still becomes to 0.5, but the reason I wrote it this time was so that you could see which number relates to which number and why I put it in this order. So you get negative, and that's the whole point, 17 divided by 0.5, which comes out to negative 34. Why negative 34? Because it's at this point, after 2.5 hours here, 2.5 hours hits the biggest crowd, and then the crowd starts to go down, which means it's for the first time that the slope is negative, or is decreasing. Before that, the crowds were increasing, and that's what that positive responses showed. Crowds were always increasing. You can actually punch this into Desmos, and it can actually come up with a pretty close drawing, but I'm not going to. Determine we did that. What do these numbers represent? We talked about it. What does positive and negative rates of change mean? We talked about it. Okay. Number 5. So always read your questions fairly well. It says the cumulative distance traveled over several days of the 2007 Tour de France bicycle race is shown in this table. Calculate the average rate of change and cumulative difference between consecutive days. So they want you to calculate the average rate of change here, and then here, and then here, and then here. Now the nice thing is the delta x is going to be 1 day each time. So you're always going to be divided by 1. So you can pretty much ignore your delta x. And you just need to focus on the change of your delta y. Well, I can write that right there, 203 plus. It went up 2/3. So they did a total distance of plus 203. So I know that the difference between these y's is 203, and the difference between the x's is 1. So it's 203 divided by 1. Then on this next day, it's 396 minus the 203. And the difference here is, and let me do it in typing so I can show you the differences. It's essentially first differences. So I get 203 on the first one. The next one I'm going to get 193, and the next one I'm going to get 165, and the next one I'm going to get 200, 100. That's a tough one. 40. That was 740. It would be 179, but it's not. I believe that's right. And then the next one is 230. 211. No, sorry. 219.5, 218.5, I think. Yeah. And then the next one is 154, 56, 156 to the next one. So you can see that because the x's went up by 1, that I could figure out the slopes right here. And you can also see that they were always positive. So let's see this. Oh, damn it. This one's related to that. 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 This one's related to those two. This one's related to these two. And this one's related to the last one. But you can see it's positive the whole way. And you can also see it's roughly, 176.8. So they were pretty consistent. The first day, if you look at it, the first day they got steeper, then a little less steeper, and then quite a less steeper. So these probably represent hills, because if you can go further on this day, you probably had a harder distance to go on this day. And then they went really long, and their longest best achievement was between leg 4 day and 4th and 5th day. So this is probably the flattest part where they could cover the biggest distance. And then this last stretch here, they did the smallest amount, which means it's probably very mountainous. Tour de France loves going up the mountains. And so they could only cover a small distance. Does the Tour de France travel over the same distance each day? Explain. No. And that probably means that the paths they had to do were either hilly or very crowded, or there were obstacles. But hilly is the most likely explanation. And if you know the Tour de France, you'll get it. What is the average rate of change in the values of this function? So there's a straight line. So it's going to be the slope no matter what. Yeah, that it's a straight line. So because the rate of change between here, the delta x is 4, you're going to discover that the delta y is 24 minus 8, which is 16 divided by 4, which is 4. You're going to discover that you're going to get the same slope when you do the delta x and delta y between this. What does that indicate? That it's a straight line, or straight between those. But if you want to see it in writing, here it is. So for the first one, we're dealing with f of x is equal to 4x. So when x is 2, 4 times 2, y is equal to 8. When x is 6, 4 times 6 is equal to 24, which is equal to y. Which means that y2 minus y1 divided by x2 minus x1 is equal to 24 minus 8 divided by 6 minus 2, which is equal to 16 divided by 4, which is equal to 4. And guess what? That's the slope in front of the line, which just goes to show you the rate of change in a line is consistent. When x is equal to 2, we found out y is equal to 8. We found that out in the last one. When x is equal to 26, y is 4 times that, which is equal to 104. The delta y for this is 104 minus 8, which is equal to 96. The delta x for this is 26 minus 2, which is equal to 24. And you're going to discover that when you take delta y over delta x, you're going to get 96 divided by 24, which is 4. So no matter where I take my 2 points on a straight line, I will always get a slope, which makes sense from what we've learned about straight lines. The slope is always written right there. So no matter what 2 points I get, I'm always going to get 4, because that's the slope of the line. Well, the results don't necessarily tell me it's a straight line, because you can get that result on a parabola. You can get the same slope on 2 spots on a parabola. Well, that's not accurate, but you can definitely on a cubic. I can get a slope here that's the same as the slope here. If you take endless points and you always get 4, then yeah, we're talking about a straight line or a direct relationship. Ooh, Shelley's phone plan. So we'll do number 7. Actually, I'm just going to go down a little bit so I can get number 8 in this as well for next time. Okay, here's Shelley's phone plan. Okay, so she has a cell phone that starts at $39 per month, and she gets 250 free minutes. I think we've already discussed this, and any minute she uses over 250 free costs 10 cents. The function is described as this. This is how much it costs her below 250, and this is the function that cost her above. So that would be $39 plus 0.1 times m minus 250, because she gets the first 250 as part of her 39 bucks. So that means she gets charged 10 cents for every minute above 250, which makes sense. Can be used to determine her monthly cell bill, where C of m is her monthly cost and m is the number of dollars. Discuss how the average rate of change as she talks. Okay, that's easy. For the first 250 minutes, she will be consistently paying a flat line, $39, no matter what. That's what it'll look like. For the first 250 minutes, it'll be flat line, which means the rate of change is 0. All lines, horizontal lines, have a slope of 0. All vertical lines have a slope that cannot be calculated. but all flat lines have a slope, horizontal lines have a slope of 0. At this point, it becomes a line that uses this formula. I know this doesn't look like a line, but if you were to distribute it, it would indeed be a line that becomes 0.1x instead of m minus 25 plus 39. How did I get the minus 25? That's 0.1 times negative 250, which becomes 0.1x plus 14. This is clearly a line whose slope is 0.1, which means the slope, no matter what point I take in here, the rate of change is going to be 0.1, which makes sense because she's charged 10 cents per minute, which is the slope, 10 cents per minute. So after 250, the slope is going to be 0.1. Before 250, the slope is going to be 0. And that's true no matter what spot on that line I take. And you can represent this as f of x is equal to 39 as long as the x values are smaller than x and smaller or equal to 250. Okay. There it is up there. Okay. And there it is ending. And then you can do a second value that is equal to 0.1 times x minus 250 plus the $39 for values of 250 is smaller than x. There we go. And there's the two functions. And anywhere, any delta y, delta x I do on this will get me a slope of 0.1, and any delta y and x I do on this horizontal will get me a slope of 0. There. That shows it a bit more accurately. Looks like a steep slope, but that's only because the x values are going up by 50. If I change the steps of this to something smaller, like 5, the slope would get smaller. Didn't really do it there, but let's see if I can do it. Let's get rid of that. Didn't really do it still. It's still keeping the same 50 steps down below. Probably because it can't show steps of 5. There. Now, yeah, it got a little less steep. But my point is clear. You don't need me to go on about that. That's a pretty stupid question, actually. So then they give you a population of animals. And if you look at it carefully at the numbers, it's a city. A city has grown in the population of people over years since 1950. So they're counting in 1950 as year 0. Year 0 is 1950. So like 20 years later is 1970. 80 years later is 2030. So they're trying to get predictions of where the city will be. And you can see that at the first year, they started with a population of 5, which I believe is in thousands. So 5,000 people on 00. So in 1950, they had 5,000 people. By 1960, they grew by 5,000 more. But by 1970, they grew by 10,000 more. By 1980, they grew by 20,000 more, which is the change here. By 1990, they grew by 40,000 more. So each difference, it goes 5,000, 10, 20, 40, and it goes 80, and then it's going 160. So you can see we have a growth curve, and it's doubling each time. So that means we have 2 to the power of x plus 5. This plus 5 brings us up by, it starts us at the population of 5,000. Calculate the interval rate of change in population in the following intervals. Okay, so they're going to want us to do specific intervals. By the way, what's this going to tell us? The rate of change is going to be pretty flat in the beginning, and then as we go up the line, it's pretty steep, and the steepest is going to be in the last interval here. But they're going to tell us what intervals they want. So from 0 to 20 they want, which is from here to here, and they want us to skip 10. And then they want us to do from 20 to 40, which is right there. And then they want us to do from 40 to 60, which is right here, but skipping the middle one. So you're going to get interesting slopes. And then they want us to do the whole thing from 0 to 60. So the whole thing. So they want us to take it from there to there, skipping all the numbers in between. So what are you going to get on this one? What's the slope going to be like 0 to 20? Well, let's try it. Let's draw a line between 0 and 20. You're going to get a flat line like that. You're going to get a fairly even slope, and we can even guess from our graph. 0, so it goes out here to 100 over 90. So what's 100 over 90? 100 over 90 is like 10 over 9. You're going to get a pretty flat slope. 10 over 9 is like 1.1. Okay. What are we going to get from 20 to 40? So that's from here to here, and we're going to get a slightly steeper slope. Something like that. And you can even see from our drawings it's going from 80 to 0 to over 90. So you're going to get 80 over, sorry, you're going to get 90 over 80. So you can see that the slope has gone from, and actually that first slope is probably 0.9. And now this next slope is more like 1.1. So you can see it's getting steeper. What's going to happen from 20 to 30? 20 to 30, did they actually ask us 20 to 30? 20 to 40, no, 40 to 60, sorry, 40 to 60. So 40 to 60 is right here. So you can see the line is going to be the steepest from there. And if I draw a line through that, I'm going to get like that. Close, but no cigar. But anyway, you can see that I'm going to go from 30 to, let's say, 90. So my delta x is going to be 60. But my delta y is going to be way up here at 360. So you're going to get a growth of change that's something like 6. Very steep. And then the final one is joining the first and the last dots. And it's interesting to note that it won't be as steep on that one as it will be on this second last one. That'll be the steepest one. So you're going to get increasing rates of change as you do these measurements. Is the population constant before we go answer these? No, it's clearly a growth curve. How do we figure out what it'll be in 215? What assumptions would you make? Well, you'd have to assume that the population is going to grow consistently, and you also have to say that it's going to be right here, and you'd have to sort of come up with a population. So if it's 60, it's 320. That means at 80, it's 640, and at that year that they're talking about, it's going to be 1280. So it's going to be 1 over 1 million people instead of 80,000 or 320,000. But let's see, let's do the rate of change. So what's the first one? There's the first one. What's the delta x? 0 to 20, so delta x is 20. What's the delta y? 15. So you get 15 divided by 20, which is roughly 3/4. So the m is going to be 0.75. So the average rate of change here is going to be 0.75. So that's just delta x divided by delta y divided by delta x. There's your delta y, and the tops are delta x. You can tell it over here because x here is on the x-axis, and the population here is on the y-axis. Okay, what about this one? Between these time periods, that delta x is 20. What's my delta y? It's the bottom number's 20. What's 20 divided by 20? It's clearly 1. So here, up here, Up top, the AVOC was 0.75. Down here, the AVOC is 1. So every year, 1,000 people. What about this here? Well, the delta X is between 60 and 20, or 40, which is 20. And the delta Y is much bigger, 320 minus 80. The delta Y is 240, so I'm divided by the 20. It's the same as 24 divided by 2, which is 12. Wow. Suddenly the average rate of change is 12,000 people per year. And to put it into perspective, yeah, it's 1,000 people per year. And to put it into perspective, up here, it is 750 people per year. And that's because you got to remember everything is thousands of people. And so you can see that how much more people are increasing between that last phase, as I said. And then finally, from the whole graph, you can see my delta X is 60, and my delta Y is 315. And for that, I'll need a calculator, but 315 divided by 60 is still easy to calculate. And you can see my average rate of change for this graph is that, which means my AVOC for the whole graph, AVOC from 0 to 60 years, is, which is the same as 5,250 people per year. Now, notice that the slope of this graph is much smaller overall, and that's because in the beginning, it was slow to grow, and the end it was fast, whereas the average rate of change in the last 20 years is this. Guess what the average rate of change is going to be in the next 20 years? It's going to be double that. Guess what the average rate of change is going to be for the next 20 years? It's going to be double that. And believe it or not, populations very much behave this way because in some countries they were having 7 or 8 kids per parents. So the population was actually going 4 times, not 2 times. If you go back and look at your history from the Industrial Revolution onwards, and really when they started making antibiotics and vaccines, populations really increased. Once they could cure diseases, populations really improved. Well, 250, since 0 is there, 250 is at the end of the graph, and since this rate of change between 50 and or 40 and 60 is 12,000 per year, and the population was 320, and if you notice, each 10 years the population doubles. So from 70 the population will be, let's do it like this, in year 70, we're trying to figure out year 100, population will be 640, and I might have got it wrong in that first. In year 80 the population will be 1,280,000. And in year 90, the population will be 2,000,000. Yeah, I did get it wrong. 560. And finally, by year 100, which is the 2060 they're looking for, the population will be 5,120,000 people. So you can see the population went from 5 years to 5,000 people to 5 million people in just 100 years. This is a great example of how compound interest works as well, and something you should adopt and learn while you're young. It's something I wish I had paid attention to. Is the population growth constant? Of course not, and we just did. And what assumptions have to be made? That food doesn't run out, that there's no famine, that there's no disease, that this city can accommodate these people. That's the assumptions. And that's the issues we're facing today with things like climate change. Ooh, this thing goes on. I might have to stop a little bit. During the Apollo missions, he hit a golf ball. And I might be using Desmos for some of these, even though I really want to show you how to do the calculations. I'm going to do 2 at a time. So he hit a golf ball, and it'd be easy to misinterpret this graph. This is actually a downward facing parabola because the height of the golf ball based on t should be written as this, minus 0.8 t squared, which tells you it's an up or downward facing parabola, plus 18t. And then there's plus 0. So don't forget your squared right here. So this is the y-intercept. So that tells me that we're looking at something like this. It goes up and up and up, and then down and down and down. Let's read the question first. Where h is based on time, the height is in meters, and the ball is in seconds. Determine the average rate of change over this time period, 10 seconds to 15 seconds. Well, that's not too bad. So that means if we can sort of figure out what the halfway point is, that would help. To know the halfway point, we would need to know the vertex. We could also factor, and you would be able to do that. 18 divided by 0.8. Yeah. And that would be possible as well, but we're not. And actually, you know what? I can get a good idea by ignoring this 0, because I can indeed factor out t from both. So if I factor out t minus 0.8t, I'm left with t minus, and I believe I came up with, what's 18 divided by negative 0.8? It's negative 22. Ah, there we go. So now I've come up with the vertex of this thing. We can see at 0 seconds it flew up, and that's when it hit the next x-axis it hit the ground at 22.5 seconds, which means the vertex is at 11.5 seconds, which means between 10 and 15, 10's about here, 15's about here, we're going to get a downward slope, which is interesting because the ball actually rises to here and then descends, which shows you that average rate of change over too long a distance isn't accurate to what actually is happening to the ball. But we do have our delta x right here. It's 15 minus 10. So we know that our delta x is 5. The big question is, what happens, what's my delta y? Well, for this I'm going to use Desmos, but you can use the calculation if you want. You simply take your calculator, and it's minus 0.8 t squared plus 18. And just to confirm this, you can click your home, and you will see, oh, maybe I got something wrong there. Plus 18t, sorry. You will see that indeed, from my calculation, it does indeed hit the ground at 0.222. But now the nice thing is I can take my h of 15, and it's going to give me my y value. And I can take my h of 10, it's going to be my y value. So that means that 90 is my y value. So let's do this fully. So this, at this point, it is at 10 comma, let's do it in writing because it's going to be easier. This point here is 10 comma 100. And then this point over here is 15 comma 90. So if I take delta y to 90 minus 100 over delta x, which is 15 minus 10, I get minus 10 over 5, which is a minus 2, which means it's descending 2 meters per second. That's the slope of this line here. And that is called the average rate of change, which is the same as the slope of that secant line. Secant line is a line that joins 2 points on a graph. Pretty good question, and how you would do it manually is you would take this 15 and you'd plug it into your calculator, and you do 15 squared, and you'd multiply it by negative 0.8, and then you would add 18 times 15 to get your delta y of 90. Sorry, of 10. So 10 squared is 100 times negative 0.8 is negative 80, and then 10 times this is plus 180. So you get plus 100, which is what we got. And then you would take your 15 seconds, you would square that, you'd multiply it by negative 0.8, and then you'd add 18 times 15, which would give you 90, which is what we got. Then you do what we just did. That's how you do it manually on a test. You would just plug your 15 seconds into the formula and your 10 seconds into the formula to get your y2 and your y1. I just use Desmos because I'm not going to necessarily sit there. So a company that sells sweatshirts finds that the profit can be modeled based on the profit is in thousands of dollars based on the number of sweatshirts sold, which is in S units, and it's expressed in thousands of units as well. This is a downward facing parabola, and look at that, it has a y-intercept there. So what we're going to discover with this one is that it's going to cross the y-intercept at 0, right there, 0, comma, 11.15, which means it's going to go up to a peak and then come down. And y represents profit. So that's 11.5 times 1,000. That's $11,150 if they sell 0 t-shirts, which is kind of weird. But you can see their profit's going to rise up, and there's going to hit a peak, and then it's going to descend, and they're going to hit a negative. Now you could figure out the negative by taking the root of that, but only do what you have to. Calculate the average rate of change in profit for the following. So you're taking between 1 and 2 seconds, or sorry, 1 and 2 units, so from here to here. So you're going to take probably have a rate of change that's increasing. From 2 to 3, from here to here, and it's probably going to be starting to slope off. From 3 to 4, and I'm not sure where the turning point is. And from 4 to 5,000 units. As the number of sweatshirts sold increases, what do you notice about the average rate of change in profit? What does this mean? It means that at a certain point, when you're spending too much money on material, you're not making as much money. And so even though you're selling more t-shirts, the cost of making those shirts is more than the money you're profiting, thus your profit will start going down. You're trying to hit this profit right here, which is the maximum possible profit, and it'll tell you how many t-shirts you have to sell to make that maximum profit. Let's make our lives a little easier and put it into Desmos. We'll call it profit based on S, the number of t-shirts, is equal to negative 0.3 S squared plus 3.5 S plus 11.5, was it? Just to get an idea of what this graph, 11.15. Just to get a look at what this graph looks like. And sure enough, we wouldn't care about anything below 0. And we wouldn't really care about anything after the graph hits the bottom here. Sorry, hits the x-axis here, which is 14.72, 271 rather. 0.271. We would only really care about this part above the x-axis because that's the profitable point. Yeah, that's the profitable point. After this, and I might have made an error on when it crosses the x-axis, but after it crosses the x-axis, it's no longer profitable. And you should actually figure out where that is exactly instead of what I've done. So I'm just going to extend it a bit more just to go past. Yeah, it says it's 0.4. Let's just add a, it says it's 271. Let's add 2.8 just to have the exact point. So you can from the graph, thanks to Desmos, you can actually see when it's going to peak, and it's going to peak when they sell 5,833 shirts. They're going to make $21,358. So that's what really the number of shirts they should make. Now normally, to figure out your delta X and your delta Y, you would, and actually maybe I'll do it like this. You could make a table, but you should plug it in. yourself. We're looking from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So you can just do 1, 2, 3, 4, and 5. And it's going to give you your y values between those points. And notice it looks like we're taking positive rates of change all the way up. And that's really the only values we would need to do our calculation. Because now we have, let's put it right there. Put this up here. And we'll put this, where are we going to put this? Right there. So now we have a table right here where we can calculate our delta x over and over again. And notice our delta x is 1 each time. And all we have to do is figure out our delta y to get an idea of the slope between each of these points. But it's very easy to see that the slope of this line here, drawn between these points, is going to be less steep. It's going to be less steep than the slopes drawn between these points here, which is going to be much steeper, which means that their profit rate of change is bigger here, but not their max profit. And as your profit is slowing down, you know that you're approaching peak profit. Essentially, that's what it means. But let's do our delta y and delta x. Well, each time our delta x is going to be 1, but we're going to do our delta y for the first one, which is between 1 and 2. And when you do your calculator, you're going to discover that's 2.6 divided by 1. So that means we're making 2,600 shirts, $2,600 per shirt at that point. That is part A1. At A2, our delta y is 16.95 minus 18.95 minus 16.95, which is 2. And remember, it's $2,000 per shirt. Now, why did the profit decrease there? Well, because as we're approaching our peak, the number of shirts don't yield us as many dollars. We were making lots more money in the beginning, and that could also reflect demand. As more people have our shirts, fewer people have to buy it. Between 3 and 4 seconds, and I should actually say that's between, let me increase this. Let me actually say that's between 1,000 shirts to 2,000 shirts. That's our average rate of change. And I multiplied by 1,000 to get a better idea. Between 2,000 shirts and 3,000 shirts, our AVOC is $22,000 per shirt. Between 3,000 shirts and 4,000 shirts, it's 20.35 minus 18.95, which is the same as 1.4. 4 per shirt, which is, the AVOC is $1,400 per shirt. And then finally, your last one, your A4, is between 4,000 shirts and 5,000 shirts. Your AVOC is equal to the difference of 21.15 minus 20.35, all divided by delta x of 1, which is the same as, let's see, 0.65, 0.7, 0.8, 0.8, which means you're making $800 per shirt in the last stretch. To verify it, just take your delta y2 minus y1, x divided by x2 minus x1 to figure out your slope between each of these points, and you will indeed get, it won't come out as 2,600, it'll come out as 2.6, 2.0, 1.4, and 0.8. But you got to remember that it's in thousands of sweatshirts per thousands of dollars per sweatshirt, which is why I've translated it to that. And it's actually per thousands of shirts. So you're actually making $2.60. That's actually better to look at it that way. In part 1, you're making $2.60 per shirt. In part 2, you're making $2 per shirt. Yeah, it shouldn't be per shirt here. I got that wrong. In part 3, you're making $1.40 per shirt, and in part 4, you're making 80 cents per shirt. That's because I forgot that it's not per shirt, it's per thousands of shirts. So even though I'm making $2,600, that's per 1,000 shirts, so it comes down to $2.6 per shirt. So this is actually more accurate, not that. And so what does, as the number of switches sold increases, what do you notice about the average rate of change? Well, it's going down. What does that mean? Well, either it means demand's going down, or cost to make the shirts is going up. So maybe cotton costs more, maybe. Or maybe labor costs more. Maybe people demanded a raise. So either factor is evident. Another excuse could be competition. Somebody opened a better, so demand, that would include demand though. Demand's going down. So either that's competition. Competition might have opened up. Or people don't care. Maybe it was a trend. Maybe it was a meme on the shirts. Maybe it's a trend. Maybe people don't buy that type of shirt anymore. That happens. Maybe some scandal happened. Maybe the CEO got caught killing an elephant and all the shirts have elephants on it. Who knows? Predict the rate of change will stay positive and explain what that means. No, it won't, because I know this is a parabola and because I know I'm going up the right side of it, the left side of it. I know it's a downward facing parabola. So if I have positive slope, I know I'm approaching the vertex. Since I'm approaching the vertex, after I pass it, I know I'm going to have a negative slope on the other side. So I mean, that tells me that as I get closer to the max profit, my vertex is going to get smaller. By the way, you can also set up Desmos to calculate your delta x's. For instance, this would be a formula for, let's call it AVOC. AVOC, let's just call it A, is going to be your f of x2 minus your f of x1 divided by, and let's put that all up top in brackets, divided by, let's put just the right side in brackets. So you can see, what am I doing here? I'm making a slope divided by, and then I can just put my x2 and see if it can do it. Divided by x2 minus x1. And I can just do that. And I can maybe do x1 is equal to 1, and I can make my x2 2. And actually, let's just plug it right in here. So I can just say between 2 and 1 is going to be the same as 2 minus, it's always going to be 1 down here. And you can get your slope. Jesus is going to just give me a value. So that's the slope of that line, but is it going to give me the slope? So that's between this point and this point, 1 and 2. Was it F? No, it's, sorry, P of S. I got to do P of S. P of 2 minus my P of 1. And it's going to give me the slope, 2.6, and I think that's what we found. Let's see, it'll be on my drawing. Yeah, 2.6 was the first thing we found. And then I can do it again for P of 3 and P of 2, and see, it'll calculate it for me as well. And that's what we found as well, that it was 2. See, down here, 2. Next one should be 1.4. 1.4. And notice that the delta x is 1 over, and that's because we're going just up one at a time on our x values. And then finally, P5 divided by P4 is 0.8, 80 cents, just as predicted right there, 80 cents per shirt. Now I'm going to get closer. I'm going to pass the I'm going to go past the vertex on purpose. Oh, look, we're going close to the vertex because the slope's getting very small. 7, 6. Suddenly we're negative. Why is that? That's because the vertex is at 5.832. And if I go from 7, 5.832. So if I go from 7, and actually it should have even registered, no, yeah, it wouldn't register between 6 and 5 because that's a flat line. But once I go past the peak, I'm starting to go down the slope. So all the things after 5.8 will be a negative slope. -1. And what's interesting is, no, I won't say what's interesting. So now I'm essentially going down the right side of the slope. But what's nice is you can set up your own rate of change formula in Desmos instead of plugging into a calculator, so long as you show the work on your page. So you can't just write what I've written. You've got to show your delta x divided by delta y formula. Okay, next question. These are taking a little longer than I want. So this is a population of town is modeled by, that's clearly an upwards parabola. And the size of population T is years since 2000. So they're starting with 2000, and notice the population is 20,000 people. Use graphing technology. Thank you. So P based on time is equal to 50t squared plus 1000t, 50t squared plus 1000t plus 20,000 people. So let's see if it can find that for me. Now it's going to start way up here. So let's change the y-axis. Go from 0 to, I don't know, 15 years. With the y-axis, we're going to start it at 20,000. And we're going to go up to, I don't know, 120,000 by steps of 1,000. Okay, so you can see, and also we're going to make x bigger than bigger or equal to 0. Sorry, t bigger or equal to 0. And you can see that that is a parabola that's sort of going up and up and up and up. And now I have a nice little thing where I can just see my my x value will be my year, and my y value will be the population. Just make sure you understand what the size of population and number of years. And so 0, when it starts, is the year 2000. Predict the average rate of change in the population size will be greater, closer to the year 2000, or farther into the future. So the question is, does it slope up higher or slower? So you can see that this slope is getting, the rate of change is going to get higher and higher and higher as I go up. So if I'm drawing it straight from origin to there, I'm going to have a steeper slope the further I get away from the year 2000. Explain how you made your prediction. Calculate the average rate of change between these values, 20 and 2010. Okay, let's do that. 20 and 2010. Let's find out. Average rate of change is going to be P20 minus P10 divided by what's on, I did the same mistake. I got to put that in brackets. Close brackets. And what's 20 minus 10? It's 10. So it's going to show me the average rate of change is 2,500 people per year. That's how quickly it is growing. And you can even do the spot 20 comma P20, and it'll label it. And you can do the spot 10 comma P10, and it'll label it. So there you go. And you can theoretically even draw a line between those points using the rate of change. So you got a line of 2,500 and it starts up at 35,000. Let's see if that'll work. 2500x. Almost. And then I also have to subtract x minus 10, which is where I start. There you go. I'm able to draw a secant between those 2 points using the slope I discovered, how much I had to transition x to the right, and how much I had to raise y, which is here and here. And now I've drawn a secant right between it. And the rate of change is 2,500 people per year. Now all I have to do is find the numbers I'm using, and remember that 2,000 counts as year 0. So the next one is between year 12 and year 2. So year 12 and year 2, and then don't forget to change your delta x, 12 minus 2. And I get 1,700, and I can even plot those points, 12 comma P12, and 2 comma P2. So there's those points. Now I have to adjust my new slope is 1,700, and I have to adjust my new x adjustment is 2, and I also had to go look at it's 2,200 there, so I got to add 22,200, and boom, now I have a secant line that goes through those 2 points to show me roughly what the slope looks like between those 2 years. The average rate of change between those 10 years is slower than the 10 years between 2010 and 2020. Then this wants a 10-year span between 2015 and 2005, so that's year 15 and year 5. So I'm looking at year 15, delta y when x is 15, delta y when x is 5. And then don't forget you've actually got to change it down here, 15 minus 5. I could just write in the division here, but I'm trying to show you the delta x, delta 5. And between that time period, and I'm going to skip the dots and the lines, there's a rate of change of 2,000. And then the last one they want is between 10 years between 2010 and 2020. So that's between year 20 and year 10. And it's between 20x and 10x. And you can see that's one of the steepest rates of change, 2,500. And that's over here between 2010 and 2020. Now, you could draw graphs in there over and over again and show why some are steep. And yeah, my earlier prediction is correct. You could also theoretically draw 2 lines, and it would always take a while. You'd have to put one line would be at 0 comma p of 0. So that's the very beginning. And your second line would have to be at, well, let's call it the variable d comma p of d. And I'd add a slider and a label. Now I can put my slider, my new dot, anywhere I want, and I can just go from 0 to whatever year I want. Let's say 50, step of 1. So now I've got this wonderful, I can put this second dot anywhere. Then I can draw a line that's going to be y, and this is tricky, y minus, is it y minus d? Y minus p of d is equal to the slope, oh man, open brackets, p of d minus p of 0, close brackets, divided by d minus 0 times x, and it's going to be x, actually, yeah, x minus d, I think, times x minus d. There we go. Now, that was complicated. If you can follow that, great. But now I have a dot I can slide, and it will draw the secant line between any dot I slide, I draw, and I can also tell it to read out the slope. I can call the slope S. No, let's call it, yeah, S is equal to this calculation right here. And it will tell me the slope as I slide that line. This is fantastic because now I can calculate, and if you can even make a sliding line here, but I can calculate the slope between origin, or the beginning of the graph, and all the way up to 50 years. I can even make that farther. I can make that all the way up to 100 years. And you can see the slope gets bigger and bigger the further and further I go. You could have also added a slope here, and then you could have even calculated any 2 years that you wanted. You just have to add more variables. If you followed what I did there, good for you. But my point is, you can make these tools that make your life a lot easier, depending on what your study is. Your classmate was absent today and phones you for help. Share your with your class 2 reals when someone might calculate an average. Real life example. Biking away from your home and biking towards you, or driving to work, driving home from work. When might it be useful? Probably analyzing your savings over a long period of time. And how would you explain it? You're taking the slope between 2 points on a curve, and then once you find that slope, you can see how quickly those 2 points are changing. Vehicles lose value over time. A car purchased for this much, but is worth only this after 8 years. What is the average annual rate of change for the value of a car as a percentage? Oh, tough. And I'm not going to do 14. That's a tough one. It's an interesting one, and it's a valuable lesson. Cars always are a bad investment. And that's how you know people are crazy, because it's the first thing they want to buy. The first thing you should be buying is real estate or stocks. So it's going like this, and it reaches this in 8 years. So that means at year 0, when time is 0, value, which is value at year 0, is 23,500. And by time 8, value at time 8 is equal to 87.50. So how do you calculate the rate of change? Well, delta y, V8 minus V0 divided by x2 minus x1, which is 8, minus 0. So this is going to be equal to 87.50 minus 23,500 divided by 8, which is equal to minus 13. I'm not going to bother with it. I'm going to do 87.50 minus 23,500. So it depreciated this much divided by 8, which is equal to this. So it depreciates that many dollars per year. So the question is, what is the average annual rate of change in the value of cars percentage? So how would you calculate the percentage now? We have to go back and look at the value of the car and look at how much you're losing as a percentage of that value of the car. So it would be this number divided by that number times 100. Anytime you're looking at a percentage, it's a portion of something multiplied by 100. So you're taking that and you're dividing it by the original value of the car, which is 23,500, and you're multiplying that by 100. So the percentage value of the car that you're losing, depending on what decimal point he wants. Oh, I got that wrong. Copy it. Is negative 7.85%. So he's losing 7.85% value of the car every year, which makes sense. And I believe you could graph that as, sorry about this crazy thing I did. You could graph that as value over time is equal to the initial value of the car minus 7.85, so you turn that into decimal, 23.5, minus 0.7, what was it? Wasn't 0.0785. That's the decimal version of 7.85%, times 23,500 times t. So you can see that after 12.73 years, you totally lose the value of the car. And after 0 years, and now let's see if v of 8 gives us the value they gave us. Oh, capital V. 87.42. Is that what the car depreciated to? Close. 87.50. So it's because I rounded up the percentage. If I didn't, if I wanted more accurate, I would have left all those decimals in my percentage to give a very good idea. But this is essentially a steady decrease in the value of the car, and you can find the years mentioned. And look at that. After, it's not really true, but after 12.7 years, your car is worthless. And that's not really true, because cars don't lose 7% over and over and over again. They lose a percentage of last year's value, not the initial value. Okay. No. And then the function here models the relationship between a vehicle speed and fuel economy. In other words, this is a downward-facing parabola, which means there's a maximum fuel costs based on economy of fuel X. So that means you're going to you're going to get the most kilometers per liter at a certain speed, X. So X is the speed, and f of X, the vertex Y value, the top of the Y value, will give you the best fuel economy. So if you put this into a Desmos, and you do fuel economy based on gas, or based on liters per kilometer, is negative 0.005 x squared plus 0.8x plus 12, you will get a parabola. And it will reach a peak, and then it will come down. Now, because you got to read the question carefully, vehicle speed and fuel economy. F of X is the fuel economy in kilometers per liter. So you get the most kilometers per liter, the higher your y-axis goes. And X is the speed. So that means at 0 kilometers, you're getting 12 liters per kilometer. And as you reach here, you hit the vertex. And that means at 80 kilometers for this car, you hit your maximum fuel economy, 80 kilometers per hour. And then as you go faster and faster, which is true, as you hit over 100, I think it is, most cars lose on fuel. I think the cruising speed, perfect cruising speed is 50 or 80, 50 or 70 on average. And then when you hit 173 kilometers per hour, technically your gas is just flying out of the car. And it's actually not possible to hit 0 fuel economy, because otherwise your car would just stop. But it's just kind of showing a rough idea of, after a certain speed, your car is burning too much gas per kilometer. You're not getting the best efficiency out of it. So the best cruising speed to go the longest distance is 80 kilometers an hour in this model. And then it wants you to figure out 10 kilometer intervals in speed and use your results to determine the speed that gives you the best fuel economy. Yikes. So they don't even want you to graph it. So you can see this graph is useful. But I could do this too. I can give a 10-kilometer intervals. Do I really want to do that? So I can say A, or rate of change, R, is going to be, open brackets, F of it's called A minus F of B divided by A minus B. And I can just set these, that at 0 and this at, or that at 10 and this at 0. And it's going to give me, why did it give me, radius. I can't use R. Let's call it economy. No, I can't use E either. Let's call it fuel. And I got 10 and I got 0. It should give me, F of X, no, G of X, which is my new one, is equal to that. But it should give me specific values when my G of it's just, I just want a value called G. So you can see between 10 and 0, my fuel economy is 0.5, and you're going to discover that you're trying to hit 0 of fuel economy because you want the slope of your line to be 0. So I'm going to change this to 20, and actually I could just do minus F of A minus 20. Sorry, minus 10, and that should do it. A minus 10. Since it's always going to be different by 10. And then I can skip my B, and then I can see, and now I got to add different ranges. It's got to go all the way from 0 to 150, let's say, by steps of 10. So at 0, there, 10, I get 0.75, 0.65, and I'm trying to reach G. I'm trying to get this down to 0. So somewhere between there, 80 and 90, it's saying is one thing. So from 80 and 90 it gets negative, and right between those two, so between 80 and 90, it's saying is my best option, and we know it's 80. And that's because at 90 to 80, so at 90 it's giving me the slope downwards. So pretty much 80 is giving me the right answer. So you can see if you do it by 10, but you'll get a much more accurate idea if you do it by 5, and you do these steps by 5. So you can see 85, you can see right at 75, right as soon as you go past 80, it gets negative. That should pretty much tell you that 80 is the sweet spot. And if you understand what I did here, I'm essentially taking differences that are 5 apart instead of 10 and dividing it by a delta x of 5. But it's plugging it into this equation, and it's giving me a thing called G, which is essentially a slope of the line between these 2 points. Because this here is the slope of a line, and I'm using this little a to change the value of f of x as I go along, because it just would take too long. I strongly suggest you use the calculator and take a few values by 10 between 0 and 10, and then, for instance, you can do it like this, 0 and f of 0, and it's going to be divided by 10, and you can see you're going to get the same results. So if you take it between 20 kilometers an hour and 10 kilometers an hour, you can see you're going to get the same results that I got. And the delta y is always 10 because you're going 10 at a time up here in the x values. And that's a hint too that as we progress, the delta x down below is going to become a consistent value. And you're going to get the same thing I got, that when you hit 80, and really here's the clue right here, between 81 and 79, you're going to should see a slope of 0. Yeah, and that's because between those 2 points, which is 81 and f of 81, 79, and f of 79, if you draw a straight line through them, you will get a flat line. And that's because the vertex is at 80. So this is sloping downwards, this is sloping upwards, and they will give you a flat line at the vertex of late. If I draw a line between that, the slope is going to be 0. And that is because the vertex is at 80, which is on equal sides of 79 and 81. You get the same results if you change this to 80.1 and 80.1 and 79.9 and 79.9. You will discover that they are flat. You're going to get a g of 0. Can't divide it by the difference now is 0.2. But the slope is still going to be 0. No matter what, and that's because these two up here will come out to 0. Do it yourself, you'll see. And that's it. Estimating is when you kind of do what we're doing, when you understand the graphs that are going on.